Now we are in the second part of the second tutorial session. We had been practicing certain numerical problems on the friction, moment of inertia, gravity in the first part. Here I will focus more on the stress, strain and residual stresses. Just to recall certain relations and formula, stress, it is denoted by sigma, is force per unit area, where F is force applied and A is the cross sectional area of the body. Your units of the stress are in Pascal or in Newton per meter square. Strain is deformation per unit length, that is the change in length per unit, the initial length, where delta is in the change in length and L naught is the initial length. Units are dimensionless, or sometimes it is expressed in percentage strain, the percentage elongation, or maybe in compression the percentage compression. Hooke's law was also discussed, that is the relationship between stress and strains. We know sigma is equal to E into epsilon, where E is the Young modulus of a material for which the units are Pascal. Residual stresses are the stresses that remain in a material. It remain in a material after the original cause of the stress has been removed even. So, sources of the residual stress are manufacturing processes such as welding, machining and heat treatment. Measurement of residual stress is often using the X-ray diffraction or hole drilling, and many optical methods are there that helps us to find the residual stresses in the bodies, and these residual stresses also determine the properties and the applications where the bodies are to be used. Let us now try to see some of the numerical problems on the relations which were discussed in the previous weeks. So, this is a problem statement where it is given a square steel rod of 20 mm into 20 mm in section is to carry an axial load which is compressive of 100 kilonewton. We need to calculate the shortening in a length of 50 mm. I will try to show you the tensile strength test, compression test and some other tests in the forthcoming weeks. We will try to use these relations to find out what is a Young's modulus, what is the tensile strength, compressive strength, impact strength of various materials. So, because it is a square rod, so we need to find a shortening in a length, that is we need to find the value of delta L. So, here delta L is to be determined, the shortening in the length. What we are given are area is equal to, it is given in mm. So, I convert the mm into meter, that is 0.02 into 0.02 is equal to 0.0004 meter square, and I have gotten length, this is area, length which I denote by L, this is equal to 50 mm, in meters is equal to 0.05 meters. Load that is given is, I will denote it by P, this is equal to 100 kilonewton. E is also given, that is Young's modulus, which is equal to 2.14 into 10 raised to power 8 kilonewton per meter square. Now, to find the shortening of the rod L, we need more space. Shortening of rod L, that is delta L I need to determine. We know stress sigma is equal to P by A, that is load per unit area. This is equal to 100 is the load and area is 0.0004 meter square. 100 kilonewton is the load. Area is 0.0004 meter square. So, this turns out to be 25000 kilonewton per meter square. This is stress. Now, strain, we know that E is equal to stress by strain. Therefore, strain is equal to stress by E, which is equal to 25,000 by the value of E, which is given as 2.14 into 10 raised to power 8. So, this strain is delta L by L, which is 25,000 by 2.14 into 10 raised to power 8. So, therefore, delta L is equal to 25,000 by 2.14 into 10 raised to power 8 into L. Length given is 0.05. This is equal to 25,000 by 2.14 into 10 raised to power 8 into 0.05. This is equal to 0 point, because 10 raised to power 8 is here, 0.0000584 meter. It is better to put it in millimeters. So, this into 10 raised to power 3, this is equal to, or I would write, or this is equal to 0.0584 millimeter. So, shortening of the rod, that is delta L, that is shortening, is equal to 0.0584 millimeters. This is the answer. I have a similar problem statement here, where a hollow cast iron cylinder 4 meter long, 300 millimeter outer diameter and thickness of metal 50 millimeter is subjected to a central load on the top when standing straight. The stress produces 75,000 kilonewton per meter square. Assume Young's modulus for cast iron as 1.5 into 10 raised to power 8 kilonewton per meter square, and find magnitude of the load, longitudinal strain produced, and total decrease in length. This problem also I will solve for you. Here it is given the outer dia, I will put it as D, is equal to 300 millimeter, which is equal to 0.3 meter. Thickness T is equal to 50 millimeter, which is equal to 0.05 meters. Length L is equal to 4 meter, 4 meter long rod, right. Now, we have the stress that is produced, that is given. Stress that is produced, that is sigma is equal to 75,000 kilonewton per meter cube. And we have been given the Young's modulus here as well. Young's modulus value is 1.5 into 10 raised to power 8 kilonewton per meter square. Now, inner diameter of the cylinder is to be determined. Inner diameter would be small d, which is equal to outer diameter minus 2 times into thickness. For instance, this is a cylinder here, this is outer dia d, this is inner dia small d, this is thickness. Thickness is here 2 times, this is T, T. So, this is d minus 2 of T, this is equal to 0.3 minus 2 into 0.005, this is equal to 0.2 meter. This is my inner dia. Now let us start solving the problems that it has asked. Magnitude of the load. Magnitude of the load I need to determine. I will try to solve it here. Magnitude of load, that is, if I know that sigma is equal to P by A, that is load per unit area. So I need to find P is equal to sigma into A, that is stress into area, which is equal to 75,000 into the area. Now this area is pi by 4 because this is cylinder. This is d square minus d square, that is outer dia minus smaller dia, right. So this is equal to 75,000 into pi by 4, outer dia is 0.3 square minus inner dia is 0.2 square. Here I calculate the value of P equal to 2945.2 kilonewtons. So this is first part, magnitude of the load. Right. Second part is longitudinal strain produced. Now second part, that is longitudinal strain. For this I need to find longitudinal strain produced. I denote it as E. Here E is equal to stress by Young's modulus, which is equal to 75,000 by the value of the Young's modulus, 1.5 into 10 raised to power 8, which is equal to 0.0005. There are no units, strain is dimensionless. Now decrease in length is the third part. That is delta L, like the previous numerical. To find the value of delta L, I know strain is delta L by L, right. So and I know the value of L here, that is 4 meter. I know the value of the strain here. So that means the strain that I have just calculated as 0.0005 is equal to delta L by 4, which gives me delta L is equal to 4 into 0.0005. This is equal to 0.002 meter. So this meters, if I convert into centimeter, this is multiplied by 10 raised to power 3. This turns out to be 2 millimeter. So this is decrease in length. Right. So this is all solved now. Now there are numericals in the similar fashion that I have here. For instance, there is a safe stress for a hollow steel column which carries an axial load of 2.1 into 10 to the power 3 kilonewton, and this safe stress is 125 meganewton per meter square. The external diameter of the column is 30 centimeters. Determine the internal diameter. You will use a similar relation as I did in the previous numerical. So this is again a hollow steel column. So we have external dia, we have internal dia, like we had it here, the external and the internal diameters, right. So you will try to solve this numerical, you will find the solution in the lecture notes and try to compare how have you determined, how have you calculated it. We might have to use some relationships which have been given in the theory part of the lectures covered in week 2 and 3, and then you have to find the solution to this numerical problem. Similarly, I have given you another numerical statement here. Find the Young's modulus of a brass rod where diameter is 25 millimeter and length is 250 millimeter. which is subjected to a tensile load of 50 kilonewton when the extension of the rod is equal to 0.3 millimeter. For this, we have to find the Young's modulus. You know the relationship of the Young's modulus that has been used in the previous numericals as well. So here you might have to first find the area of the rod. The diameter is given, the area of the rod is to be taken. So dia is given, area would be question mark. Then you have to find the tensile load. Tensile load is already given. So the length is already given. You will find the stress. Stress you will find. Based upon the stress, then you will find the strain. Strain you will find, strain E. Then based upon the stress and strain, you will try to find the value of Young modulus, that is stress per unit strain, that you try to find here, and try to compare the answer that you get with the answer which I give you in the lecture notes. Then there is another problem statement where a hydraulic press exerts a total load of 3.5 meganewton. This load is carried by two steel rods supporting the upper head of the press. If the safe stress is 85 megapascal and Young's modulus is 210 kilonewton per millimeter square, find number 1 diameter of the rods, number 2 extension in each rod in a length of 2.5 meter. To find the diameter of the rod, you first have to find area over which the load is being applied. So load carried by the two rods has to be determined, that is value of P is to be determined. So based upon the value of the P, then calculate the total area, stress is given, you will finally find the diameter of the rods, that is D you will find accordingly. Second part is extension in the rod. Once you know the diameter of the rod, so then you will use the Young's modulus relation, that is stress by strain. So you will put the value of stress here and strain here, that is P by A over delta L by L. This relation you will use for Young's modulus to find finally the value of delta L. So these problems you will solve. Now another thing that we discussed in the previous weeks are Hooke's law. Hooke's law, Young's modulus, these were discussed. The elasticity of the material is given here. Young's modulus is the measure of material stiffness. The units is Pascal, is already discussed. Next is Poisson's ratio. The definition is ratio of transverse strain to axial strain. So transverse strain to axial strain ratio is Poisson ratio. Typical values are 0.25 to 0.35 for most metal. Let us try to see some problem statements on this. A steel rod of cross-sectional area 2 centimeter is subjected to a tensile force of this. Calculate the stress in the rod. This is a kid's play. We have gotten the area A is equal to 2 centimeter square, which is equal to 2 into 10 raised to power minus 4 meter square. Force is equal to 10,000 Newton. So stress is equal to force per unit area. This is equal to 10,000 by 2 into 10 raised to power minus 4, which is equal to 50 megapascal. This was just again a warm up. Similarly, there are the small, very short numericals. 1 meter long aluminum bar is stretched by 0.2 millimeter under a tensile load. Consider this strain. Strain is change in length over original length. It could be directly determined. It is 0.2 over 1 meter. That is 0.02% strain would come as an answer. I have given very short numericals here because some problems might also come in your exams which will be very short. To get marks in your exam, these problems would be easy for you to score. Now comes another problem statement where we need to determine the yield stress, ultimate tensile stress, percentage reduction in area, percentage elongation. When we are given a mild steel rod of 12 millimeter diameter, which was tested for tensile strength with a gauge length of 60 millimeter. Following observations were recorded. Final length is 80 millimeter. final diameter is 7 millimeter, yield load is 3.4 kilonewton and ultimate load is 6.1 kilonewton. Now, we need to determine the following parameters: yield stress, ultimate tensile stress, percentage reduction in area, percentage elongation. So, we have been given here d diameter is equal to 12 mm, we have been given length is equal to 60 mm, and recorded observations, the final length that we have gotten. Final length I will put it as capital L, that is 80 mm. Final diameter is D is equal to 7 millimeter. Yield load is 3.4 kilonewton. I will put it as W yield is equal to 3.4 kilonewton, which I convert into Newton, that is 3400 Newton, and I have gotten ultimate load, that is W ultimate is equal to 6.1 kilonewton, which is equal to 6100 Newton. These are all the given values. Now, I need to find the yield stress first. To find that, let me first find the original area of the rod. Original area, that is A is equal to pi by 4 d square is equal to pi by 4 into 12 square is equal to 113. I keep it in millimeters only, millimeter square. Then I have gotten the final area here in the calculations. Final area small a is equal to pi by 4, the final diameter, which is smaller one, that is small d. This is equal to pi by 4, small d is 7 square, this is equal to 38.5 millimeter square. Now, let us try to find the solutions to the questions which are given. First is yield stress. Yield stress, we know yield stress is equal to load, that is the yield load per unit initial area. This is equal to 3400 by 113. This turns out to be 30.1 Newton per mm square, or I can put it as this is equal to 30.1 megapascal. Second point is ultimate tensile stress, that is ultimate tensile stress. So, this is again calculated in the similar fashion. We have ultimate load per unit area, this is equal to 6100 by 113, this is equal to 54 Newton per millimeter square, or this is equal to 54 megapascal. Next point that is asked is percentage reduction in area. So, percentage reduction in area, it is so simple. We have the initial area and the reduction in area, that is A minus A. This is in percentage, we will calculate, that is 113 minus final area is 38.5, that we have calculated by the initial area itself. This is equal to 0.66. In percentages, we can call it 66%, right. fourth point it has asked is percentage elongation. Percentage elongation is again so simple. We have the final length L and change in length. So, change in length is 80 minus 60, the final length is 80, this is equal to 0.25, or I can say this is 25%. Right? These kind of problem statements keep coming when we try to talk about stress, strain curve or elasticity. We will also try to solve something in Poisson ratio now. So, in Poisson ratio you see this numerical statement that is there, a 2.0 mm long metal wire is loaded, resulting in a 4 millimeter elongation. Find the change in diameter of wire when elongated if diameter of wire is 1.5 millimeter and Poisson ratio of wire is 0.24. Just to recall once again, Poisson ratio is the transverse strain by axial strain. This is my Poisson ratio. Now, to calculate the Poisson ratio, what we have here is the given values are the length of wire as 2.0 meters only. The change in length is also given 4 millimeter. So, if I turn it to meters, it is equal to 0.004 meters. Diameter of wire is given, diameter of wire is 1.5 millimeters. So, I have diameter of wire D is equal to 1.5 millimeter and I have been given Poisson ratio, that is 0.24. The longitudinal strain, find the change in diameter of wire when elongated by this diameter, right. So, longitudinal strain, let me determine first. Right, this is equal to change in length by original length, this is equal to 0.004 by 2.0, this is equal to 0.002. So, longitudinal strain I have gotten, right. Now, to find the change in diameter of wire, right, I need to find the changed diameter. So, let me try to see here using Poisson ratio, we have mu is equal to lateral strain by longitudinal strain, it is axial strain or longitudinal strain, right. So, that means 0.24 is equal to lateral strain by 0.002, that is the longitudinal strain given. So, this gives me the value of lateral strain or the transverse strain as 0.24 into 0.002, which is 0.00048. Using this, I will find the change in diameter. So, lateral strain is this. So, lateral strain, this is also equal to change in diameter per unit original diameter. So, that is equal to 0.00048 is equal to change in diameter by original diameter is 1.5 mm. So, I got the change in the diameter as 1.5 into 0.0048, which is equal to 0.00072. So, this is my answer, right. So, using the Poisson ratio, I found the ratio between the lateral strain and longitudinal strain, that is the ratio between the transverse strain and the axial strain. Using the relation, I found the change in diameter when I was given the length of the wire, the resulting elongation that was given, and also the diameter of the wire was given, and the Poisson ratio was given. So using the Poisson ratio, I calculated the change in diameter. The similar problems could be taken like another one, when a brass rod of 6 millimeter is subjected to a tension of 5 into 10 raised to the power 3 Newton, the diameter changes by 3.6 into 10 raised to the power -4. Calculate the longitudinal strain and Poisson's ratio for brass, given that Y for the brass is 9 into 10 raised to the power 10 Newton per meter square, that is the elastic modulus is also given. So we have been given here diameter, we have been given here tension, we need to find the longitudinal strain. Again, using the Poisson ratio relation, similar to the pattern that we did in the previous numericals, you can try to solve this numerical, right, and find the answer. You can compare your answer again with the solution that I give you in the lecture notes. Okay, there is another problem statement where metal wire of length 1.5 meter is loaded and elongation is 2 millimeters. If the diameter of wire is 1 millimeter, find the change in the diameter of the wire when it is elongated. We have been given here that the Poisson ratio is 0.24. This is almost exactly similar to what I just did here, right. So this also you can try to solve. So there is another problem statement in which Young's modulus is given as 110 giganewtons per meter square. This shear modulus is 42 giganewtons per meter square. Find the bulk modulus and lateral contraction of a round bar of 37.5 millimeter diameter and 2.4 meter length when stretched 2.5 millimeter. This is an interesting problem where we have been given value of E as 110 giganewton per meter square, Young's modulus. We have been given the shear modulus. Shear modulus I denote it as C, that is 42 giganewtons per meter square. We have been given also the diameter 37.5, that is diameter of bar is 37.5 millimeter. So because all other things are in meter, I will also convert this into meter. This is equal to 0.0375 meters. Length of the round bar is also given, that is L is equal to 2.4 meters. I have to find bulk modulus and lateral contraction, right. This is 1, this is 2. So bulk modulus K for this relation, K is bulk modulus where K is equal to M into E by 3 into M minus 2. Here shear modulus is also given. For shear modulus also there is a relation that also will put here. Shear modulus, for that the relation is E is equal to 2C 1 plus 1 by M, right. Let us try to first find the value of M using the shear modulus, right. This is relation 1, this is relation 2. So using 2, I just put the values. E, it is 110 giganewton is given. I'll convert this into Newton into 10 raised to power 9. This is equal to 2 into C. C is 42 giganewtons, that is 42 into 10 raised to power 9 into 1 plus 1 by M, 1 plus 1 by M, right. So this gives me the value of M as, if you solve this equation, it will give you M is 1 by 0.31, which is equal to 3.22. Now substituting the value of M, substituting in 1, relation 1. Right, I got it here. K is equal to value of m, that is 3.22 into E. Value of E is 110 into 10 raised to power 9 by 3 into m minus 2, that is 3.22 minus 2. This is equal to 96.77 giganewtons per meter cube. So, I have gotten the value of the bulk modulus. First part is over. Next comes the lateral contraction. For the lateral contraction, that is change in the diameter, delta D. Here I have also been given the value of the delta L, that is delta L is given here, that is equal to 2.5 mm. This is equal to 0.0025 meters. So, for lateral contraction, I come back here. I first find the longitudinal strain. Longitudinal strain, that is delta L by L is equal to 0.0025 by the length, that is 2.4. This is equal to 0.00104. So, lateral strain is equal to longitudinal strain into 1 by m. Lateral strain is equal to longitudinal strain, that is 0.00104 into 1 by m. This turns out to be 0.00104 by 3.22. This is equal to 0.000323. So, this gives me the value of the delta D. Now, lateral contraction delta D is equal to lateral strain into D, that is 0.000323 into D. D is 37.5, which is equal to 0.121 millimeters. Right. So, this is one where we have calculated the bulk modulus, and also we have used the relationship for the shear modulus as well in this problem. So, the last problem statement in this lecture is where we have been given the steel wire of 100 centimeter length and cross sectional area of 0.03 centimeter square, and load that is applied on this is 100 Newton, and this is slower load that is being applied. The Young's modulus of steel is also given, that is 2 into 10 raised to power 11 Newton per meter square. We need to calculate the work done, in stretching, right. That means we need to calculate the energy stored. So, I will just put it here, work done is equal to energy stored, right. This you will calculate by yourself and try to compare the result. With this, I am ending this tutorial, and I will meet you further. We will take you to further practice sessions, and also I will discuss about the laboratory sessions. Laboratory sessions means I will show you the videos on how different tests are being conducted in laboratory, and also we will try to see some simulations on the results on different tests which are there in the forthcoming lectures. And further, we will also try to talk about certain mechanisms in the forthcoming lectures in the forthcoming weeks. Thank you.